Okay, so in this video, we're going to be talking about Huffman code, a sort of an application of a greedy algorithm. So let me give you a few note about the context of the problem. So um, our problem is that we have, for example, a text, right? So for example, the phrase, "This is an example." And now we want to store it in our computer. But now the problem is that our computer works with bits, right? So either 0 or 1, um, and we have to figure out a way to encode these letters into bit notations, the 0 or 1s, right? And so what is the optimal mapping that would save our storage capacity? And that would be the problem um, we're to look at. Right? So one obvious solution is to use a fixed length code. So for example, we allocate, for example, 4 bits per letter, right? 4 bits per letter, and uh, we would use different combinations to create different unique codes so that we can decode it easily afterwards, right? So for example here, this is the example. Then in this table below, I extracted all the unique characters, T, H, I, S, and so on. And then for each of them, I assign a unique 4-bit code. Okay. And the entire example, this is an example, this phrase would take 72 bits to store. Well, that's not so bad, right? Like, if we have to store the entire 24 letters of the alphabet, then it only takes us 5 bits per letter, per characters, in order to create unique a bit code for those characters. So it's not impossible. But here we ask questions: can we do better? And yes, we can do better. So that's the idea of Huffman code. So Huffman code is first of all a variable length code. So before we have seen that we can allocate a fixed length of bits for each characters, but with Huffman code we can vary the length of the code. Like you can have a character with only 1 bit, or another character with 5 bits, or another character with 3 bits. So up to you to decide. However, there's another condition, which is a Huffman code is a prefix code. So what a prefix code means is that none of the letter is a prefix of any other word code. So I'll show you an example. So this is the Huffman code table of the phrase "this is an example." And as you can see, the shorter codes like I only has 3 bits, or S only has 3 bits, can never be a subset, the beginning subset of another code, longer code, right? So 0, 1, 1, there would be no other code that would start with 0, 1, 1. Otherwise, your machine would just get confused when it's trying to decode the bit code, right? So it needs to be unique, and no code word would be a prefix of any other code. Okay, so now, so by doing that, we save a little bit. So the entire phrase "this is an example" only takes 63 bits to store. Well, you can do the math, uh, but so it saves us around, well, 9 bits, a little bit, but if we scale it to a larger document, then it would save us a lot of memory. So now I would like to illustrate how to construct a table of Huffman code given a string of characters, characters we want to code, and the frequencies of appearance of these characters, and here the Huffman code. Um, so do you remember the idea of the prefix code? The idea of prefix code means that um, uh, none of the code work is a prefix of any other code. So now if we build a tree where this is not a binary search tree, right? Where if we go left, it means 0, go right, it means 1. So here, if we go left, it means 0, and here we code this A, so A is 0, B, for example, is 0, 1, 0, and 0, we go right, we go left, and we go right, so 0, 1, 0, 1, and B here, and C, and so on and so forth. So it's the idea of a tree, um, in order to that store the Huffman code. Um, and I told you earlier that because of the idea of the prefix code, then if, think about it, if no code word is a prefix of any other, it means that all of the letters would be on the leaves of the tree, right? So if you have like a, 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 a letter here, then it can be either this letter or this letter, and you add some more numbers, become C, and it won't be a prefix code anymore. So keep it in mind. So this is a binary tree where 0 means go left, 1 means go right, and all of the characters are on the leaves. Very good. And okay, so what would go into these uh, little circle in squares? And here, so it would be the frequency of appearance. So for example, 45, A appeared 45 times, so here I coded 45 over here, C appeared 12 times, B appeared 13 times, and the parents, the value of the parents would be the sum of the children. So 14 is the sum of 5 plus 9, 30 is the sum of 14 plus 16, and so on and so forth. Okay. Um, so what's good about this Huffman code thing? If you notice from the tree, the word that appear on the upper level of the tree, so A is on the higher level, then C or B or F, these tend to have a higher frequency. So A appears 45 times, and F here down the tree only appears 5 times. And the idea is that because you are at the top of the tree, so the code will be shorter than the one on the bottom of the tree, which would have longer codes, right? So F would finally have what the code of F is 1100, so which has 4 bits, whereas A only has 1 bit to store, right? Require 1 bit to store. And the idea is that because these letters appear so much, so if we try to use the smallest amount of bits possible to store these, we will be able to save a lot of space. That's the idea of Huffman code. So now I would like to talk about how to build such a tree. So we start with a list of characters that we want to code. Um, so here I have F, E, C, B, D, A, and from left to right I arrange them in the order of ascending frequency. So 5, 9, 12, 13, 16, 45. Right? And so I'm using the example from the textbook, just so you know. And this is the level I call the stage. So you'll see how useful it will be later with the algorithm. But basically, the idea of the stage is that we just consider things that are on this level, and things below it will be already done. So first of all, I consider the first two characters that have the lowest frequency, which is F and E, frequency 5 and frequency 9. I consider D2. And I combine them to make a parent. So 5 plus 9 is 14, right? And then I rank them accordingly on the stage level. You see? uh, I combine 5 and 9 to a pair of notes, 14, and then rank them on the stage level. And now I don't need to consider 5 and 9 anymore. I just need to consider these notes on the stage level. And so as you can guess, the next two notes that I'm gonna consider is C and B, which is 12 and 13, right? And the resulting note would be 25, and I will rank them accordingly too. Consider these two, and then I rank them accordingly. And then the next one would be 14, this note, and D, which is 16. So combine them together again, and then make a note 13, and then I combine these two, 25 and 30, to make a 55, and then last but not least, I combine these two together and make a complete binary tree. Okay, so this is done. So this looks similar to what uh, we've looked at, and from this you can easily build a code table. So A would be 0, C would be, because you go right, so 1, 0, and 0. B would be 1, 0, 1. Right? Just remember, go left is 0 and go right is 1. And this tree can be served by the computer to decode also. Okay, so now let's take a look at the pseudocode provided in your textbook about how to build a Huffman tree. So first of all, n equals c. Okay, a little absolute. So this means the length of n. Okay, of the c is c is the input, or the input of function is this, is the list of all the frequencies of appearance of our characters. So we take the length of it, and then we start. Okay, this is important. Q is a mean heap. Okay, a mean heap. So if you remember mean heap, the the smallest value will be on the top of the heap, and then the parents can never be greater than the children. You remember that heap thing. So Q will be a mean heap, and the value we pass onto the mean heap, of course, you already know, is the frequency of each characters. Okay. So for I equal 1 to n minus 1. So you may well stop here a little bit and think about why from I equal 1 to n minus 1. And if you notice, because at each stage we find two nodes, right, and combine them together to create one node. So on the stage, if you look at the stage, then at each iteration, the number of nodes on the stage will be decreased by 1, right? Will decrease by 1. And as a result, you have n minus 1 iteration. Yeah, okay? And so, this is what that means, line number 3. And for the next 4 lines, what it's basically saying is that you extract the top of the mean heap, okay, call that x, and that would be the left child of the parent node z, and then you extract the next element from the mean heap, also called as y, going to be the right child, and the value of z, the new node, would just be the sum of the frequency of its left child x and right child y. And then obviously you insert that into the queue. And because you remember, if you already pop out x and y, then these two will disappear in queue. So you pop out 2 and you push in 1, which means that at each stage, the number of nodes on the stage, in this case in queue, will just diminish by 1. Okay, and then you return the root of the node. Okay, so that's just a short demo of the Huffman code algorithm. And good luck with your class, and let us know if you have any questions.